All right, welcome to General Relativity in Geometric Algebra, Episode 4, Einstein's Equations. So, to discuss Einstein's equations, we must first derive the curvature tensors. The first tensor is the Riemann tensor, and it arises naturally when considering curvature. You might remember from other series that curvature is typically computed using the commutator of a derivative or gradient, and this is exactly how we get the Riemann tensor. Specifically, oh, my pen's working. Specifically, we consider the following. We consider for M, which is just an arbitrary multivector that is in the spacetime algebra. So now we say that M is just some multivector. We consider the covariant gradient wedged with the covariant gradient all times M, or rather than times, this is acting on this. The covariant derivatives here are acting on the multivector M. So we can expand this, and this is just going to be G mu into, we can expand it into the coordinate basis. G mu d mu, all acting on M. And then we can factor these out into the wedge product because these are scalars, recall. These are scalars. And this right here is just these are the actual vectors. So we can factor out the vectors into a wedge product, and we can factor the partial or these covariant derivatives into a commutator, because when the when the basis of the object is anti-commuting with another basis object, then also or so are the coefficients. But recall just real quick, I'm gonna put a little thing here. There's a little definition, is that the commutator of two things, A and B, is 1/2 AB minus BA. In our convention, we're using this factor of 1/2 because it's more natural in geometric algebra. I don't know if you can hear that, but that auto vacuum is emptying itself really loud. Okay, so when we factor it into two things, because of this factor of 1/2, we want to cancel it. So we have a factor of 2. We have G mu wedge, G nu, and then times that, we have the commutator of these two objects. And then all of this is acting on the multivector M. So how are we going to continue with this? We actually have to first expand this. So we must now expand 2 times the commutator of the covariant derivatives acting on some multivector M. So if we just copy this, because I don't want to write it twice, this is just going to be d mu d nu minus d nu d mu acting on M. This in the center. And then we can plug this in, d mu, and then just for clarity's sake, I'm going to emphasize that they're acting on each other successively. So this acts first on M, then this acts on the entire thing. And likewise here. And so these objects, even though this has a scalar component, it can anti-commute, or it can have a non-commutative part acting on M because it's a derivative. So it's an operator, not just some blade. Okay, so now we can plug in the definition of the covariant derivative for both of these. So we're going to have d mu acting on partial nu m plus then omega nu m minus, and I'm just going to copy this whole thing and change the coefficients. So now it's nu mu mu. And then we're going to do this one more time. We're going to plug in the definition here and here. So we get a fairly lengthy expression, as you'll see. We get partial nu m plus partial mu of the entire, um, what do you call it? The entire commutator, and then plus the commutator, omega mu partial nu m, then plus the commutator of a commutator, omega mu, omega nu m, and then we're going to have minus partial mu m minus partial nu, and then omega mu m minus omega nu partial mu m, and minus, and then we have one last commutator, but I'm going to move everything over here so that it fits. Minus the commutator of omega nu with the commutator omega mu m. As you can see, this is a fairly lengthy expression, but we're going to simplify things in order to get a more workable a more workable version of this, because doing all these terms seems pretty complicated. Well, the first thing to notice is actually this and this cancel out because partial derivatives commute with each other. And so the derivative, by definition of partial derivatives, these are the same object. And so you have it minus itself, it's 0. So we can say, but partial nu minus, or yeah, m minus partial mu m equals 0 by definition. So now we must separately expand the following. We must separately expand, oh shoot, this minus this, and then this, or this term, minus this term. So now we're going to separately expand these terms in the series, or not in the series, but in this equation right here. This one's actually the easiest to expand. Well, it's not like they're actually both relatively easy. They just this one has more steps in it, but this one is you get it in just 2 lines essentially. So, or 2 or 3 lines. So first, we have partial mu of omega nu m, then plus omega mu partial nu, then minus partial nu omega mu m minus omega nu partial mu m. And then I'm just going to give a little bit of motivation for maybe seeing what the answer is, being able to see what the answer is without actually doing all this math. Because if you know, if you recognize the patterns, you'll actually be able to just go directly to the answer from this. And that's because when you take the derivative of this entire thing, you do the product rule, where if you have, say, the derivative of AB, then that's equal to the derivative acting on A, and then plus the derivative acting on B. And so you have those two objects. And so you can imagine that you're going to get partial mu, you're going to get an object that just has partial mu acting on M. And if that's the case, then it would have a positive sign, and this has a negative sign, and that's exactly this. So you're going to just have that this term will cancel with this. One of the terms from here will cancel with this, and then one of the terms from here will cancel with this. So you should be able to just predict that from looking at it now, but I'll expand it out just so you can see it explicitly. So expanding this out, the first term is d mu omega nu m, because recall that these are scalar. So plus omega nu partial mu m. You can already see here's the term that will cancel with this. And so what we're going to actually do is copy and paste it right here so that it's really obvious that they're canceling. And then we're going to just have minus partial, or I'm going to expand this term, minus partial nu omega mu m minus omega mu partial nu m. And then this is just this is just the complement to this other term. So we're just going to copy and paste that in, show that those directly cancel. And so you get the only things left over are this partial mu omega nu m plus the partial, or sorry, minus the partial nu omega mu m. However, the commutator product is distributive. And so we can just combine this into a single commutator. And that's going to be d mu omega nu minus d nu omega mu, commuting with m. Let me put this there. Okay. So this is the first thing we needed to expand. And now we're going to do the second one. So second, we're going to expand this term. And this has more steps, but it's pretty straightforward, actually. So that we're going to directly go or insert this definition here. So we're going to get a factor of 1 over 2, 1 over 2. So 1 over 4. Why do we have 1 over 4? It's because we have two commutators. So I'm going to apply that definition immediately to take us to this form of 1 over 4. And it's going to now be, we're going to have this times this entire commutator and this entire commutator. So omega mu of the entire commutator of omega nu m minus m omega nu, then it's going to be minus omega nu m plus or minus m omega nu omega mu. So that's the first. It's the first term. We can just copy and paste this. Nope. Copy and put a minus plus, and then swap all of the indices. So it goes mu, 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 mu. Okay, so that's the first expansion. So you can already see that it's a simple expansion, but there are lots of terms. So we get 1 over 4, and we're just going to distribute through. So we get first omega mu omega nu m minus omega mu m omega nu, and then we're going to get minus omega nu m omega mu plus m omega nu omega mu, and then minus omega nu omega mu m plus omega nu m omega mu, then plus omega mu m omega nu, and then minus m omega mu omega nu. And now we're going to have a bunch of terms cancel, namely all these sandwich terms will cancel. So this mu nu cancels with this mu nu, this nu mu cancels this, then cancels with this term. So now we're just going to be left with these um, the quadratic terms, not the sandwiching terms. Though technically a sandwich is a quadratic, but don't mind me. So now we just have omega mu omega nu m plus, or I'm going to, just to emphasize, I'm now going to bring the term with m on the right side over here. So now we have omega nu omega mu m, and then plus, or rather I'll do minus m omega mu omega nu plus m omega nu omega mu. So now I'm going to apply the definition of a commutator again. I'm going to do the reverse thing. So again, using this equation. So now we just have a factor of 1 over 2, and we're going to have commutator of omega mu and omega nu times m, and then minus m times omega mu omega nu. And you'll notice that this is just the definition of another commutator. So we can apply this again, and we get the commutator of the commutator omega mu omega nu m. So we can, this is the second thing we wanted to show. The second thing. So now we can move on to our original task, which was expanding just the commutator of the gradients, or not gradients, the derivatives. So therefore, because of 1 and 2, we have 2 times the commutator of the covariant derivatives acting on some multivector M gives us, and we're just going to copy. So, oh, that's not the, I'm going to just copy this. And then this. I don't like that positioning. Like this. Okay, that's better. It's still going a little down, but whatever. We can now simplify this because recall, both of these are commutators and now they're acting both on M, so it's distributive. So we can combine this into a single commutator that is, I can do this a little cleaner. D mu omega nu d nu omega mu plus the commutator of omega mu omega nu. All of this acting on M via a commutator. And this is the definition of the Riemann tensor mu nu with M. So this is the Riemann tensor. Specifically, it is a bivector. So this is the Riemann bivector. And you can see, you can recall from the past video where these omegas were telling you, or here, I'll just go up to the definition of the omega. These omegas were telling you how the coordinate frames were changing based on the, or how they were changing. So these kind of contain the curvature in them. They don't give you the curvature directly, but they contain the information of the curvature. To find the curvature, you find out how going in different directions. Now, if you have you have two of these connection bivectors, and you see how they change with respect to each other, both in the derivatives and then with how they commute, then this gives you the total curvature. And so that is why this is then the Riemann tensor, which is the curvature tensor, or it's a bivector in this case. And don't let these mu nus get you confused. This is not the traditional form for the Riemann tensor. I will give you that in a second, but these mu nus do not correspond to the traditional mu nus in the Riemann tensor. So let's talk a little bit about this. And it's going to be this. So the Riemann tensor is defined as R with a bivector argument, and this is just more simply denoted with R mu nu. So notice that these indices aren't the like tensor indices. They're indices that correspond to the bivector argument going in and what the coordinate directions are. Okay, so that's the definition of it. But then we can also just plug in this. And how would this look in the traditional form? Well, to do that, we need to express it in a bivector basis. And that would then just be this. So we get R mu nu, then alpha beta G alpha wedge G beta. And so now we've expressed this is a scalar and this is the bivector. So because this is scalar, this is now the actual traditional Riemann tensor. And these alpha beta indices are the indices that you would normally see in traditional general relativity. So just for emphasis, I'm going to make a better arrow than that. This is the traditional Riemann tensor. Let's go a little closer. And just for sake of consistency, we can also express this in the tetrad basis. It's funny. The source that I used to learn all of this was like, you can see how in the tetrad basis that the alpha beta indices anti-commute, but they do in this one too, because this is also a bivector. So I just found that a little funny. It's like, yeah, these do anti-commute because this is a bivector. It's just one of the, while it was a good source, it has a lot of typos in it. And there were some just, and some errors where you can see they might be new to geometric algebra. Anyway, there's also not just the Riemann tensor, there's going to be something called the Ricci tensor. So there's also the Ricci tensor. Ricci tensor, which pops out when considering the curvature of or rather along a coordinate basis, G mu. So this we take this to consider the curvature acting on G mu, and this then gives us the G mu wedge G nu of R mu nu G mu, or rather G nu. So I'm just going to put this nu here. So I get this. And by definition, this is the inner product between a bivector and a vector. So this returns a vector. So we get G mu wedge G nu, and this is R mu nu dotted with G nu. Oops. Come on. There we go. And we can simplify this such that we have G mu nu, G mu wedge G nu, and then this is times R mu. So this R mu is the Ricci tensor, which is also called the Ricci vector now. So just like this can be called the Riemann bivector, this is the Ricci vector. So this implies, or actually, let me put it in the center. This implies that R mu is defined as the Riemann bivector with one of its indices dotted out. Then something, or hang on, I didn't do I didn't do the consistent thing. It's R defined as G with a single argument, or R with a single argument. So now, or with a vector argument, not a bivector argument. So even though R kind of defines, it looks like it might be the same thing as the Riemann tensor. Notice that the Riemann tensor has a bivector argument, so this is a bivector, whereas this has a vector argument, so this is a vector. And there's also the Ricci scalar. The Ricci scalar. And that is typically written with a curly r, and it's defined as the inner product between g mu and the Ricci vector. We can also express this in terms of the Riemann bivector. Okay, that was interesting. I didn't know that when I receive a call, it cancels my recording. So, yeah, I'm gonna have to edit those two bits together. But yes, we can also express this in terms of the Riemann bivector. So we then have to expand this out. So we get R mu nu dotted with G nu. And then we can use the fact that this is anti-commutative to then bring this over like so. And then we can then pull this out to have an outer product between these two. And then it'll be the inner product of two bivectors together. And because of the minus sign, this G nu is actually going to go out onto the left-hand side. And so we end up with G nu wedge. Actually, we end up with G nu wedge G mu dotted with R mu nu. And so you can express the Ricci scalar as the inner product of the Ricci vector and a coordinate basis, or you can do that with the the bivector, the coordinate bivector basis, dotted with the the Riemann bivector. Okay, and so now we have all of the curvature tensors that we need to discuss Einstein's equations. Let's summarize this though. So therefore, we have we have the following. So we have the Riemann, we have the Riemann bivector that is defined as R mu nu, which is just the derivatives and the commutators of the connection bivectors. Then we have the Ricci vector, which is just R mu, and that's just going to be R mu nu dotted with G nu. Can do a better nu. And then we have, lastly, the Ricci scalar. And that is just going to be cursive R, which is R mu, or sorry, it's going to be G mu dotted with the Ricci vector, or we can have G nu wedge G mu dotted with the Riemann bivector. So now we can talk about what Einstein's equations are after we then define the Einstein tensor. The Einstein tensor, and really it's a vector. So the Einstein vector is as follows. It is G mu equals just the Ricci vector R mu minus 1/2, then the coordinate G mu, all times the Ricci scalar. So this is the Einstein tensor, and you can also represent this in a coordinate-free basis, and that is going to be G of A. So if A is a vector, this is a vector in spacetime, then this is going to be equal to the Ricci vector r of a minus 1 half this vector, and then the Ricci scalar, which will also depend on this a. So the Einstein tensor, or the Einstein vector, is defined as this. And now we get to the Einstein equations. So if T mu, which is a vector, so if T mu, and just to emphasize that it's a vector, we have 1, 3, and if this is the stress energy tensor, and this is just a vector, so the stress energy tensor is just a vector, then Einstein's equations are, and I say are, but really it's one equation, and it's just this. It's G mu equals kappa, and this is just some constant coefficient, I'll explain it in a second, is equal to the stress energy tensor plus the coordinate basis times lambda, and we'll talk about what these are in a second. And if you want to express this in the coordinate-free form, then it would be G of A is going to be equal to kappa times T of A, and then plus A lambda. Again, we'll talk about what this lambda is in a second. Where kappa, which is equal to 8 pi g, where this g is, even though it has the same notation as the Einstein tensor, this g is actually Newton's constant of gravitation, and all of that over c to the fourth, and this is approximately 2.077 times 10 to the negative 43rd, and this is in units of 1 over newtons. And this is the Einstein coefficient, the Einstein, or constant rather, the Einstein constant. And lambda here is the cosmological constant. And so these are the Einstein equations for general relativity in geometric algebra. It's just telling you that the curvature, g, so the Einstein tensor is just the curvature. It's telling you that the curvature is equal to some proportion of the stress energy of the system plus some constant. And originally, when Einstein created this, he added this term so that he could artificially define the universe as static and not expanding, not contracting. But then when it was discovered uh, that there was expansion, it turned out that this needed to be used, even though Einstein at some point went back and just got rid of this. And so at some point when Einstein originally proposed his equations, there was this factor, and then he got rid of it and said it was the biggest mistake of his life. And then it turned out that it was necessary and he was right to have it in the first place, just for a different reason. So this is what accounts for the fact that the universe is accelerating in its expansion. But yeah, it's just literally saying that the vector that tells you where all of the energy is going to manifest itself as the curvature. And that's how Einstein led to this revolution in gravitation, where it's now viewed as the curvature of space, which is rather elegant working in the space-time algebra, getting this as a result. And let's now just give an example of what the stress energy tensor could be. So an example of T mu is T mu equal to 1 over 2 F G mu F reverse. where F is a bivector in the spacetime algebra, and it is the electromagnetic field. And so you could imagine that it's actually relatively easy to solve these equations in geometric algebra. And that's, I don't know about easy, but that's what we'll cover in the next video.